Now we can generalize the linear least squares to a regular least square regression, actually, because we learned single linear regression, single polynomial regression, and multiple linear regression. We learned all of these, and all of them have the same features of solving or same solving process, so we can generalize this. We can generalize all the polynomials here as a polynomial like this, a general linear least squares model. You can see a0, z0, a1, z1, a2, z2, and these z's are actually the basis functions, and the basis functions are dependent on the x's. X's are the independent variables. And for linear regression, if you remember, we only have this should be 1 because only have a0, and x1 should be z1 should be x1. So we only have this data. Of course, we can have more than 2 variables, so z2 can be x2 up to xm. And if we don't have these only x1, then it's just this data. So this is for linear regression. For polynomial regression, we will have power values. So x to the power 0, x to the power 2, x to the power m over here. And of course, we can have further nonlinear examples. We can simply change these z basis functions with different terms from these functions. For example, cosine and sine functions. Then we can have a Fourier function. So you can fit this as well by using these only over here. Of course, there can be some models which is not in the format above, like this, an exponential with a0. Maybe this is just the basis function here, the rest is 0. You can think of like that, but for a1 we have an exponential to the power here, so that's a little bit not fitting or not obeying this rule, so these can be considered separately. But for these three especially, we can have a generalized formulation like this. Z basis functions are these, observed values are y's, coefficients are a's, and the residuals are e's. So by using these, we can create a linear least square regression formulation to solve the set of equations. Let's check that in the next slide. The solution for general least squares will have the minimization of some of the squares of the residuals again. So these are the regression function coefficients multiplied by the basis functions we mentioned in the previous slide, and sum of squares will give us the residuals. Minimize it, meaning take the partial derivatives with respect to each of the coefficients, unknown coefficients. Then set the resulting equations equal to 0, which gives us normal equations in matrix form. These are called normal equations. So basically it's actually z times a is equivalent y. Then we can use zt transpose of them. And the matrix inverse can be employed to solve it. So basically isolate this by taking inverse of it. So put it here as well, like this. And a's are the unknown coefficients. But this is an inefficient approach for solving a set of simulation equations because we use the inverse of it. So instead we can use Gaussian elimination to make it more efficient. However, from a statistical perspective, we might be interested in obtaining the inverse and examining the coefficients, because with the inverse we can understand if the matrix is ill-conditioned or not. And LU decomposition is another method to solve. We can use this as well, but the computed coefficients can be highly susceptible to round-off errors, so we have to be careful on that too. As a consequence, more sophisticated orthogonalization algorithms such as QR factorization are available to circumvent this problem. This is not a topic of this course, but you should know that there is such a solving procedure, QR factorization, for this generalized form of the least squares, let's say. In this slide, we will talk about some statistical aspects, also the error of the general least squares formulation. If you remember from the previous slide, we actually are using the inverse of the z basis function matrices to be able to get the unknown coefficients with this formulation. And the diagonal elements of this unknown coefficients, sorry, not the unknown coefficients, but the basis function matrices is defined as zi diagonals, and this represents inverse. And the variance for the coefficients that we obtain from here can be calculated by the ZII, the diagonals of the Z basis functions, matrices, and the standard error square. Covariance is similar. It's also the same, like this, the same calculation. And we can calculate confidence intervals, the lower and upper bounds. So if you remember, the lower bound and upper bound was calculated for a limited sample using the t distribution. So we have the same here. And we have also a standard error of coefficient, which is the root square of variance actually. So we use A0, the first coefficient, minus and plus the t distribution for a significance level. And this is the number of samples, minus 2. And S is the standard error we calculated from here and root square of it. This is lower and upper bounds for A0. And we can have the lower and upper bounds on the slope as well. So for A1. And this is the same. Then we use A1 to calculate the standard error. So the coefficient of determination can also be calculated using the same formulation that we have. But here we can have a little bit simplification. We can just make this 1 minus SR divided by ST, 1 minus, this is the SR and this is the ST. ST is, subtraction from the mean. And in here, this value is basically this is the sum of squares, and this can be considered as this result. Y's are our values as a vector, and these are calculated by the Z basis functions times the coefficients that we calculated here actually. From here we can calculate this and get the coefficient of determination. Again, if this is closer to 1, that means we have a good fit.